Welcome back to the Sleepy Cosmos, where we explore the universe one peaceful breath at a time. Tonight, we drift through the gentle darkness toward distant worlds, planets orbiting alien suns, places so far away that their light takes lifetimes to reach us. We call them exoplanets, worlds beyond our solar system, and they exist in numbers almost too vast to hold in your mind. Tonight, we explore 100 calming facts about these distant alien worlds, and I promise you, you don't need to remember all of them. You don't need to remember any of them, really. Just let these cosmic truths wash over you like gentle waves on a shore you'll never visit, but can always imagine. It sounds simple at first, doesn't it? Other planets, around other stars. But the deeper you fall into this question, the more infinite it becomes. Each fact is a doorway, and behind each doorway is an entire world, with skies you've never seen, sunsets in colors your eyes weren't designed to perceive, weather, patterns that would seem like magic, and perhaps, somewhere out there in all that vastness, something looking up at their own night sky, wondering the same things we wonder. You don't need to stay awake for this journey. In fact, I encourage you to close your eyes whenever it feels right. Let the words become a soft background hum, a lullaby made of distant suns and impossible worlds. If you drift away, that's exactly where you're supposed to be. The universe will still be here in the morning, patient and eternal, waiting for you to wonder about it again. If you enjoy these gentle explorations through the cosmos, if these videos help you find peace in the vastness, a like or subscribe helps this little channel reach more dreamers, more people seeking calm in the infinite. And if you'd like, leave a comment telling me where you are right now as you listen to this. A quiet bedroom in Tokyo, a rainy evening in Portland, a late shift somewhere under fluorescent lights, pretending the ceiling is full of stars. I love knowing that we're all floating here together, scattered across one small blue world, dreaming about all the others. Now, settle in, get comfortable, breathe slowly. Let your shoulders drop, let your jaw unclench, let the weight of the day begin to dissolve. You're about to hear 100 facts about worlds beyond our own, and you don't have to hold on to a single one. Just let them carry you, softly, into whatever peace you're searching for tonight. Let's begin. 1. There are more exoplanets in the universe than there are grains of sand on all of Earth's beaches. Think about that for a moment, gently. Every handful of sand you've ever held, every beach you've ever walked, every desert, every sandbox, every ancient dune and modern shore, all of it combined, doesn't come close to the number of worlds out there, spinning silently in the dark, each one unique, each one a place that exists right now, this very moment, under alien skies. Try to imagine the sheer vastness of that number. It's not just thousands or millions or even billions. We're talking about numbers so large they become almost meaningless, numbers that our minds can't truly grasp. And yet, each one of those worlds is real, a specific place with its own geology, its own weather, its own particular arrangement of atoms and molecules. 2. The first confirmed exoplanet orbiting a sun-like star was discovered in 1995. It's called 51 Pegasi b, and it changed everything. Before that moment, we wondered if planets around other stars existed at all. After that moment, we knew we weren't alone in having worlds. The universe suddenly felt more full, more alive with possibility, more like home might not be such a rare thing after all. The astronomers who made that discovery, Michel Mayor and Didier Queloz, were awarded the Nobel Prize in Physics in 2019. 24 years after their groundbreaking observation. Their patient work opened a door that can never be closed, transforming our understanding of the cosmos from speculation into certainty. 3. That first exoplanet, 51 Pegasi b, is what we call a hot Jupiter. It's a gas giant, similar to Jupiter in our own solar system, but it orbits incredibly close to its star, so close that its year, one full orbit around its sun, takes only 4 Earth days. Imagine that. 4 days, and you've circled your entire star over and over in endless swift loops through space. The planet is tidally locked, meaning one side perpetually faces the star while the other faces away into darkness. The temperatures on the day side reach over 1000 degrees Celsius, hot enough to vaporize many metals. This was shocking when it was discovered, because our models of planet formation suggested that gas giants should only form far from their stars, where it's cold enough for ice to exist. The existence of hot Jupiters forced us to completely rethink how planetary systems evolve. 4. We've confirmed the existence of more than 5,000 exoplanets as of now, and we're discovering more every week. 5,000 worlds we can point to and say, yes, that one is real, we've seen it, measured it, confirmed it exists, and that's just the beginning. That's just the ones we've managed to detect with our current technology, which is like standing on a beach and trying to spot individual candles on distant ships at night. For every planet we've confirmed, there are likely thousands more we haven't detected yet, either because they're too small, too far from their stars, or orbiting stars we haven't studied closely enough. The true number of exoplanets in our galaxy alone is estimated to be in the hundreds of billions, perhaps even exceeding the number of stars. 5. Most exoplanets are found using a method called the transit method. We watch a star, patiently, carefully, and we wait for a planet to pass in front of it from our perspective. When it does, the star's light dims, just slightly, barely noticeably, like someone walking past a distant streetlight. But that tiny dimming tells us a world is there, blocking a fraction of its sun's light, casting a shadow across light years of space. The amount of dimming tells us the size of the planet. A planet the size of Earth blocks about 1 part in 10,000 of a sun-like star's light. That's an incredibly subtle change, requiring extraordinary precision to detect. The Kepler Space Telescope could measure brightness changes as small as 20 parts per million, allowing it to find Earth-sized planets around distant stars. 6. Another method we use is called radial velocity, or the wobble method. A star doesn't stay perfectly still when it has planets. The planets pull on it, just as it pulls on them, and this creates a subtle wobble, a gentle back and forth motion. By measuring how the star's light shifts, red then blue, blue then red, as it wobbles toward and away from us, we can detect the invisible planets tugging on it, like dancers, holding hands in the dark. This method was used to discover 51 Pegasi b, that first exoplanet. The wobble caused by a Jupiter-sized planet is detectable with current instruments, but detecting the wobble from an Earth-sized planet requires extraordinarily sensitive measurements. We can now measure velocity changes as small as 1 meter per second, about walking speed, across distances of hundreds of light years. 7. There are planets made almost entirely of diamond. Carbon worlds, where the intense pressure and heat have transformed carbon into crystalline structures, whole worlds that might glitter under alien suns, hard and beautiful and utterly inhospitable, treasure beyond imagining and completely worthless, because there's no one there to value it, no market, no desire, just geology expressing itself in gemstone form across an entire planet. These diamond worlds form in carbon-rich environments, perhaps around stars that have more carbon than oxygen. On Earth, we have roughly equal amounts of carbon and oxygen, and they combine to form things like carbon dioxide and water. But in a carbon-rich system, there's leftover carbon after all the oxygen is used up, and under the right conditions of pressure and temperature, that carbon crystallizes into diamond. The surface might be graphite, slippery and dark, but beneath could be layers of pure diamond kilometers thick. 8. Some exoplanets orbit 2 stars instead of 1, like Luke Skywalker's homeworld of Tatooine. These are called circumbinary planets, and they're real. Imagine watching a sunset and seeing 2 suns sinking toward the horizon, casting double shadows, creating twilights in shades we don't have names for, painting the sky in combinations of color that human eyes have never witnessed and perhaps never will. The orbital dynamics of circumbinary planets are fascinatingly complex, The planet must orbit both stars at a distance, where the two stars appear close together, forming what's essentially a single gravitational center. If the planet orbited too close, the competing gravitational pulls from the two stars would destabilize its orbit. The stable zone for circumbinary planets is typically at least twice the distance between the two stars. These systems prove that nature can create stable planetary orbits even in what seem like chaotic conditions. 9. The nearest confirmed exoplanet to Earth is Proxima Centauri b, orbiting the closest star to our Sun. It's only 4.24 light-years away. Only. That means if you could somehow travel at the speed of light, impossible but imagine, it would still take you 4 years and almost 3 months to get there. At the speed our fastest spacecraft currently achieve, it would take tens of thousands of years, near and impossibly far, all at once. Proxima Centauri is a red dwarf star, much smaller and cooler than our Sun. The planet orbits in what might be the habitable zone, though we're not certain. It receives a similar amount of energy from its star as Earth receives from the Sun. But that energy comes in a very different form, primarily in infrared rather than visible light. If there's life there, it would have evolved under a dim red sun, and photosynthesis, if it exists, would work with red and infrared light rather than the visible spectrum that plants on Earth use. 10. Proxima Centauri b sits in what we call the habitable zone of its star. This is the distance from a star where temperatures might allow liquid water to exist on a planet's surface. Not too hot, not too cold, just right for water to be water, not ice, not steam, but that precious liquid state that, as far as we know, is essential for life as we understand it. The habitable zone's location and width depend on the star's temperature and luminosity. Around a hot, bright star like Sirius, the habitable zone is far out, perhaps where Mars is in our solar system. Around a cool red dwarf like Proxima Centauri, the habitable zone is much closer in, perhaps where Mercury is in our system. The concept seems simple, but it's actually quite complex, involving factors like atmospheric composition, greenhouse effects, cloud cover, and planetary geology. 11. The habitable zone is sometimes called the Goldilocks zone, after the fairy tale, just right, but being in the habitable zone doesn't guarantee life, or even liquid water. It just means the temperature might be suitable. A planet also needs an atmosphere, the right chemistry, protection from radiation, geological activity perhaps, and 1,000 other factors we're only beginning to understand. Mars, for instance, sits at the edge of our Sun's habitable zone, but it has almost no atmosphere and no liquid water on its surface. Venus is also near the inner edge of the habitable zone, but its thick atmosphere creates a runaway greenhouse effect, making the surface hot enough to melt lead. Being in the habitable zone is necessary, but far from sufficient for actual habitability. 12. There's a planet called 55 Cancri E that might have a surface covered in graphite and diamond, with an atmosphere full of carbon monoxide and carbon dioxide. It orbits so close to its star that its year lasts only 18 hours. 18 hours to circle an entire sun. The surface temperature reaches about 2,400 degrees Celsius, hot enough to melt iron, hot enough that the planet's surface might be an ocean of lava, glowing red and orange in eternal daylight. The extreme heat creates a strange state of matter on the surface. Silicate rocks that would be solid on Earth are molten. Elements that we think of as solids or gases might exist in exotic high-temperature forms. The day side of the planet is likely covered in a sea of liquid rock, while the night side, though still incredibly hot by Earth standards, might have a thin crust of solidified material that constantly breaks and reforms as the planet rotates. 13. Some exoplanets are rogue planets, wandering through space without a star to orbit. They were either ejected from their original solar systems by gravitational interactions, or they formed alone in the depths of space. Imagine a world drifting through the galaxy in complete darkness, no sun to warm it, No seasons, no days, no years, just endless cold night. And yet such a planet might still have internal heat, might still have geological activity, might even have liquid water beneath a frozen surface, heated from below by radioactive decay and tidal forces. These lonely worlds are incredibly difficult to detect because they emit almost no light. We find them primarily through gravitational microlensing when they pass in front of a more distant star and briefly magnify its light. Some estimates suggest there could be billions of rogue planets in our galaxy, possibly even outnumbering stars. They represent a completely different category of world, untethered from any sun, sailing through the darkness between stars for billions of years. 14. The Kepler Space Telescope, during its mission, discovered more than 2,600 confirmed exoplanets by staring at a single patch of sky and watching for the tiny dips in starlight that indicate planets passing in front of their stars. One instrument, one field of view, and thousands of new worlds. It makes you wonder what we'd find if we could watch every star, all the time, with perfect clarity. Kepler observed about 150,000 stars continuously for over 4 years. That's a tiny fraction of the stars in our galaxy, less than 1/10,000,000th of the total. Yet even in that small sample, it found thousands of planets. When we extrapolate from Kepler's results to the entire galaxy, the numbers become staggering. Nearly every star likely has at least one planet. Many have multiple planets. The galaxy is full of worlds, dense with them, packed with planetary systems as far as we can see. 15. There's a class of exoplanets called super-Earths, planets larger than Earth but smaller than Neptune. We don't have anything like them in our solar system, but they appear to be common throughout the galaxy. They might be rocky like Earth, or they might have thick atmospheres and be more like mini Neptunes. We're not sure yet. Each one is a mystery, a whole world we're only beginning to understand from billions of miles away. Super-Earths have masses between 1 and 10 times Earth's mass. Some might be scaled-up versions of Earth, with deeper oceans, higher mountains, stronger gravity. Others might be ocean worlds with no land at all. Still others might have thick hydrogen atmospheres, making them more like gas giants than rocky planets. Without visiting them or studying their atmospheres in detail, we can't be sure which category any particular super-Earth falls into. 16. One exoplanet, called HD 189733b, has winds that blow at over 5,400 miles per hour, about 7 times the speed of sound on Earth, and it rains glass there, sideways. Molten glass forms in the atmosphere, crystallizes, and then screams through the sky horizontally in those devastating winds. It's a beautiful nightmare of a world, deep blue in color like Earth, but for entirely different reasons, lethal and gorgeous. The extreme winds are driven by the temperature difference between the planet's day side and night side. The planet is tidally locked, so one hemisphere is constantly baked by the star's heat, while the other is in perpetual darkness. Heat flows from the hot side to the cold side, creating sustained supersonic winds that circle the planet in a never-ending storm. The glass rain is silicon dioxide that evaporates on the hot day side, condenses into tiny particles on the cooler night side, and then gets swept around the planet by those screaming winds. 17. The color of that planet, HD 189733b, is blue because of silicate particles in its atmosphere that scatter blue light, similar to how Earth's sky is blue. But while Earth's blue is gentle and life-giving, this blue is a warning, a sign of temperatures over 1,000 degrees and glass rain and winds that would tear apart anything we could build. If you could somehow survive on that planet's surface, protected from the heat and the glass and the winds, you would see a deep cobalt sky, darker than Earth's sky, almost navy blue. The blue color comes from Rayleigh scattering, the same phenomenon that makes Earth's sky blue, but the particles doing the scattering are not air molecules, but tiny grains of silicate glass suspended in the scorching atmosphere. 18. There are exoplanets we call hot Jupiters, gas giants that orbit very close to their stars, completing an orbit in just a few days. They shouldn't exist according to our early models of planet formation. Giant planets are supposed to form far from their stars where it's cold. But these worlds migrated inward, pulled by gravitational forces over millions of years, settling into tight orbits where they're blasted by stellar radiation, their atmospheres boiling off into space in long comet-like trails. The migration probably happened early in the system's history, when the planets were still embedded in the disk of gas and dust from which they formed. Interactions with that disk caused the planet to lose angular momentum and spiral inward. Some hot Jupiters may have formed close to where they are now, but most likely took a long journey inward from the outer reaches of their systems. 19. We've discovered planets around pulsars, the rapidly spinning corpses of dead stars. These are among the strangest worlds imaginable, orbiting dense stellar remnants that beam radiation across space like cosmic lighthouses. The first exoplanets ever detected were actually around a pulsar, discovered in 1992, 3 years before we found planets around normal stars. Worlds circling the dead, bathed in pulses of radiation, completely sterile, completely alone. Pulsars are neutron stars, the collapsed cores of massive stars that exploded as supernovae. They're incredibly dense, packing more mass than the Sun into a sphere only about 20 kilometers across. They spin rapidly, sometimes hundreds of times per second, and beam intense radiation from their magnetic poles. Any planets orbiting a pulsar would be subjected to this radiation, making life impossible. These planets may have survived the supernova that created the pulsar, or they may have formed afterward from the debris of the explosion. 20. Some exoplanets have years that last mere hours. The shortest orbital period we've found is about 4 hours for a planet called K2137b. It orbits its star so closely, so quickly, that if you stood on its surface, assuming you could survive the heat and radiation, you'd see the star massive in the sky, barely moving, the horizon and zenith occupied by burning stellar surface, day eternal and brief, all at once. The planet is probably tidally locked, so you'd always see the star in the same position in the sky. But because of the rapid orbit, you'd experience strong tidal forces, stretching the planet slightly into an egg shape. The surface gravity would fluctuate slightly as you moved around the planet. Time itself would seem strange, with a year passing in the time it takes to watch a movie, seasons compressed into minutes if they existed at all. 21. There are planets made mostly of water, which we call ocean worlds or water worlds. Not like Earth with its continents and seas, but worlds where the entire surface is an ocean hundreds of miles deep, with no land anywhere, just water above and crushing pressure below, and at the bottom, perhaps exotic forms of ice that only exist under such extreme conditions, ice that stays solid at temperatures that would boil water on Earth. These exotic ice phases have crystal structures different from ordinary ice. Ice 7, for instance, forms at very high pressures and remains solid at temperatures over 100 degrees Celsius. Below that might be Ice X, where the hydrogen atoms are squeezed so close to the oxygen atoms that the ice becomes denser and harder. At the very center of a water world, the pressure might be so intense that ice becomes metallic, conducting electricity like a metal. The ocean above would be completely dark below a certain depth, lit only by whatever bioluminescence might evolve there, assuming life could exist in such conditions. 22. The TRAPPIST-1 system contains 7 Earth-sized planets, orbiting a small, cool star about 40 light-years from Earth. 7 worlds, several of which sit in the habitable zone. It's one of the most exciting discoveries in exoplanet science because it gives us multiple targets to study, multiple chances for life, all in one system. If you stood on one of these planets, you might be able to see the other planets in the sky, some appearing larger than our moon, worlds so close together they're practically neighbors. The planets orbit very close to Their star, because the star is so small and dim, the entire system would fit inside the orbit of Mercury. The planets are so close together that they gravitationally interact, tugging on each other, causing their orbits to shift slightly over time. By carefully measuring these orbital variations, astronomers can determine the planets' masses and densities, revealing whether they're rocky, icy, or something else entirely. 23. In the TRAPPIST-1 system, the planets are so close to each other that if life evolved on one, it's theoretically possible for microbes to travel between planets on rocks ejected by asteroid impacts. Panspermia, between worlds in the same system. Life seeding itself across multiple planets, riding stone vessels through the brief darkness between neighboring worlds. When a large asteroid or comet strikes a planet, it can excavate material and launch it into space at high velocity. Some of this material might reach escape velocity and enter orbit around the star. In the TRAPPIST-1 system, where the planets orbit so close together, a rock ejected from one planet might be captured by the gravity of another planet within a few years or decades. If microbes were present in that rock, protected deep within from the radiation of space, they might survive the journey and seed life on a second world. This could mean that all 7 planets in the system share a common biology, all descended from the same origin of life. 24. Some exoplanets are tidally locked to their stars, meaning one side always faces the star in permanent day, while the other side faces away in permanent night. In between these extremes is a narrow band of eternal twilight, where temperatures might be moderate, where life, if it exists, might cluster in that ribbon of compromise between fire and ice. This twilight zone, sometimes called the Terminator line, would be a strange place to live. The sun would hang forever at the horizon, never rising, never setting. Temperature would be bearable. Not too hot, not too cold. But you'd experience perpetual red or orange light, the sun's rays coming in at a low angle, casting long shadows, creating an atmosphere of permanent dusk. Some scientists think this twilight zone might be the most habitable region on tidally locked planets, especially those around red dwarf stars. 25. On a tidally locked planet, you could walk from eternal day to eternal night, experiencing every possible shade of twilight as you travel. The day side too hot to endure, the night side too cold to survive, but somewhere in between, a zone where the sun hangs forever at the horizon, painting everything in reds and oranges and purples, never rising, never setting, just existing in perpetual dusk. As you walked from the night side toward the day side, you'd first notice a faint glow on the horizon. As you continued, that glow would brighten into a band of deep red. Further still, and oranges and yellows would appear. Eventually, you'd see the upper edge of the sun peeking over the horizon, a permanent sunrise that never completes. If you kept walking, you'd enter the day side, where the heat becomes unbearable, the sky bright, the sun glaring down from overhead. Then you could turn around and walk back into the comfortable twilight, watching the sun sink back toward the horizon as you retreat. 26. We've found planets orbiting stars that are completely different from our sun. Red dwarfs, orange dwarfs, stars larger than our sun, stars smaller, stars hotter and cooler. Planets exist around almost every type of star we've looked at. The universe doesn't care about our assumptions. It makes worlds everywhere it can. We've found planets around stars that are freshly formed, only a few million years old, still surrounded by the disk of material from which they coalesced. We've found planets around ancient stars, billions of years older than our sun, survivors of epochs when the galaxy was young. We've found planets around binary stars, triple star systems, even quadruple star systems. We've found planets in globular clusters, dense balls of ancient stars. The universe's ability to make planets seems almost unlimited, constrained only by the availability of raw materials and time. 27. Red dwarf stars are the most common type of star in the galaxy, and they live for trillions of years. If planets around red dwarfs can support life, then life might have far more time to evolve than it had on Earth. Trillions of years instead of billions. Imagine what complexity might emerge given such vast expanses of time. Our sun will die in about 5 billion years, swelling into a red giant and engulfing the inner planets. But red dwarfs burn so slowly, so steadily, that they'll still be shining long after our sun is gone. They'll outlast nearly every other type of star. If life begins on a planet around a red dwarf, it has trillions of years to evolve, to develop complexity, to perhaps become intelligent, to build civilizations, to explore space, or to go extinct and start over, repeatedly, with time for dozens or hundreds of independent origins of life. 28. But red dwarfs are also violent when they're young, producing powerful flares that could strip away the atmospheres of nearby planets. So life around red dwarfs would need to survive these early tantrums, perhaps hiding in oceans or underground, waiting for the star to calm down and settle into its trillion-year adulthood. Young red dwarfs can produce flares thousands of times more powerful than the strongest solar flares we see from our sun. These flares emit intense ultraviolet and X-ray radiation, along with streams of charged particles. A planet in the habitable zone of a red dwarf sits much closer to its star than Earth sits to the sun, which means it's fully exposed to these violent outbursts. The flares can strip away atmospheric gases, potentially leaving the planet with little or no atmosphere. For life to persist, it might need to shelter underwater or underground during the star's violent youth, emerging only after the star settles down, perhaps hundreds of millions of years later. 29. There are exoplanets larger than Jupiter, so large we're not sure if they're planets or failed stars. We call them brown dwarfs, or planetary mass objects. They blur the line between planet and star, too big to be planets in the traditional sense, too small to sustain the fusion reactions that make stars shine. They glow dimly with leftover heat from their formation, fading slowly over billions of years. Brown dwarfs form the same way stars do, collapsing from clouds of gas and dust, but they don't accumulate enough mass to ignite hydrogen fusion in their cores. The boundary between the most massive planets and the smallest brown dwarfs is fuzzy and debated. Generally, objects above about 13 Jupiter masses can fuse deuterium, a heavy form of hydrogen, and we might call those brown dwarfs. But objects below that threshold that formed by collapse might still be considered brown dwarfs rather than planets. It's a matter of formation history as much as mass. 30. The most massive planet-like object we've found is about 30 times the mass of Jupiter. At that size, it's definitely more brown dwarf than planet, but it orbits a star like a planet would, so the definitions get fuzzy. The universe doesn't care about our categories. It makes objects of all sizes and lets us figure out what to call them. These supermassive objects challenge our understanding of how planetary systems form. Did they form like planets, from a disk of material around a star? Or did they form like stars, from direct collapse of a gas cloud, and just happen to end up orbiting another star? The answer matters for understanding the diversity of objects in the universe, but the universe doesn't care about our need for clear categories. It makes what it makes, and we do our best to understand and classify it. If you're still listening, that's wonderful. If you've drifted off, that's perfect too. The universe will keep making planets, whether we're awake or asleep. Let yourself relax. Let these facts be like stars you notice and then forget, beautiful in the moment, part of a larger tapestry you don't need to memorize. Your breathing is slowing. Your thoughts are quieting. The weight of these worlds, these billions of distant spheres, doesn't burden you. Instead, it comforts you, knowing that existence is so much vaster than your worries, so much fuller than your fears. 31. We've discovered planets with multiple suns, not just binary stars, but systems with 3 or 4 stars, and planets somehow maintaining stable orbits in this complex gravitational dance. The sky on such a world would be unlike anything we can truly imagine. Multiple suns rising and setting in complex patterns, shadows pointing in 3 directions at once, photosynthesis, if it happened, evolved for a spectrum that shifts as different suns cross the sky. In a system with 3 or 4 stars, the orbital dynamics become incredibly complex. Computer simulations show that stable planetary orbits can exist, but they're restricted to specific configurations. The planet might orbit close to one star, while the other stars orbit at a distance, or the planet might orbit far from all the stars, circling the entire multi-star system. Either way, the sky would be spectacular, with multiple colored suns, each a different size and brightness, creating a constantly changing interplay of light and shadow. 32. Some exoplanets have atmospheres we can actually analyze. When a planet passes in front of its star, some of the star's light filters through the planet's atmosphere, and we can study that light to determine what chemicals are present. We've detected water vapor, sodium, potassium, and other elements in exoplanet atmospheres. We're reading the chemical signatures of alien skies from thousands of light years away. We're tasting the air of other worlds with light. The technique is called transmission spectroscopy. As starlight passes through a planet's atmosphere, certain wavelengths are absorbed by molecules and atoms in that atmosphere. Each chemical element and molecule absorbs light at specific wavelengths, creating a unique fingerprint. By measuring which wavelengths are missing or diminished in the starlight that passes through the atmosphere, we can identify what chemicals are present. It's an astonishing capability, allowing us to analyze atmospheres of worlds we'll never visit, using nothing but light that has traveled for decades or centuries to reach us. 33. The James Webb Space Telescope is now studying exoplanet atmospheres in unprecedented detail. It can detect molecules that previous telescopes couldn't see, potentially including biosignatures, chemicals that might indicate the presence of life. We're at the edge of a profound moment in history, where we might, possibly within our lifetimes, detect signs of life on another world. JWST operates primarily in infrared light, which allows it to see through dust clouds and detect heat signatures. This makes it ideal for studying exoplanet atmospheres, especially for planets that transit their stars. JWST can detect molecules like carbon dioxide, methane, water vapor, and potentially even more complex organic molecules. If we find the right combination of gases, particularly those that don't naturally coexist without being continuously replenished by life, we might have our first indirect evidence of biology beyond Earth. 34. One of the biosignatures we're looking for is oxygen in combination with methane. On Earth, both exist in our atmosphere, but they react with each other quickly. The only reason we have both is because life constantly replenishes them. If we found both oxygen and methane on an exoplanet, it might suggest biological activity, though we'd need to be careful to rule out non-biological sources to be certain before we made any announcements. Oxygen is produced by photosynthetic life on Earth, plants and algae and cyanobacteria splitting water molecules and releasing O2. Methane is produced by various life forms, including bacteria in cows' stomachs and microbes in wetlands. Without life, these gases would react together, forming carbon dioxide and water, and disappear from the atmosphere within a few million years. Their simultaneous presence suggests active replenishment, which on Earth means biology, but we have to be cautious because some geological processes can also produce these gases, and we'd need to rule out all non-biological explanations before claiming we've found life. 35. There are planets we call lava worlds, planets so close to their stars that their entire surfaces are molten, oceans of liquid rock glowing red and yellow and orange, waves of lava rising and falling, perhaps driven by tides from their nearby stars. Geology happening in real time, visible, flowing, a planet still being born or perhaps dying, it's hard to say which. On these worlds, rock behaves like water. Different minerals have different melting points, so the lava oceans would have complex chemistry, with heavier minerals sinking and lighter ones floating, creating layers and currents. The surface would be incandescently bright, glowing with its own heat. The atmosphere, if there is one, would be filled with vaporized rock, clouds of silicon and oxygen and metals, raining down as droplets of molten stone when they cool enough to condense. 36. The planet Coro T7b might be a lava world. It orbits its star every 20 hours and has a dayside temperature around 2,500 degrees Celsius. The night side is much cooler, maybe only 200 degrees below zero. This temperature difference creates intense weather, possibly including rock rain, where minerals evaporate on the passer, day side, drift to the night side, and then condense and fall as pebbles. Imagine standing on the night side and watching pebbles fall from the sky, cooling minerals that condensed from vapor clouds that came from the day side. The rocks would be warm when they land, maybe still glowing faintly. The wind would howl constantly, a supersonic jet stream carrying vaporized rock from hot to cold. The sky might glow orange from the reflected heat of the day side, visible over the horizon. The ground would be rough and rocky, covered in layers of stone that fell as rain, compressed and fused by later rain layers, building up over millions of years into strange geological formations that have no equivalent on Earth. 37. Imagine standing at the terminator line on Coro T7b, the boundary between day and night, and watching rocks rain from the sky as mineral clouds from the day side cool and precipitate. Geology turned into meteorology, the very ground of the planet cycling through the sky and back again. You'd be standing in perpetual twilight, the star forever at the horizon, its light streaming sideways across the landscape. To one side, the glow of molten lava. To the other, the cold darkness of the night side. And above, a sky filled with strange clouds, not water vapor like Earth's clouds, but silicon and iron and magnesium in gaseous form, condensing and falling, raining stone. The wind would be fierce, blowing from hot to cold, screaming past you at speeds that would make hurricanes seem gentle. The temperature would be borderline survivable if you had the right protection, too hot for comfort, but not instantly lethal. You'd be witnessing an alien weather system, meteorology operating on principles we're only beginning to understand. 38. We think some exoplanets might have underground oceans, like Jupiter's moon Europa or Saturn's moon Enceladus in our own solar system, but on a much larger scale. Entire worlds with frozen surfaces and deep, dark oceans. Beneath, warmed by tidal heating or radioactive decay, places where life might exist in eternal darkness, feeding on chemical energy instead of sunlight, thriving in conditions we're only beginning to understand might be possible. These subsurface oceans would be completely isolated from the surface, sealed beneath kilometers of ice. No sunlight would penetrate to their depths. Life, if it exists there, would depend on chemical energy, perhaps from hydrothermal vents on the ocean floor, where heat from the planet's interior drives chemical reactions. This type of life exists on Earth, in the deep ocean near hydrothermal vents, where bacteria and other organisms live without any connection to photosynthesis, forming the base of an ecosystem that includes tube worms, crabs, and fish. Similar ecosystems might exist in the dark oceans of distant exoplanets, completely independent of their suns. 39. The exoplanet GJ 1214b is likely a water world with a thick atmosphere, possibly steamy and hot like a planet-sized sauna. It's often called a mini Neptune, but it might be something we don't have in our solar system. A hybrid between a rocky world and a gas giant, something in between, something new. The planet's density suggests it's made largely of water, but it's so hot that the water exists in exotic states. Near the surface, it might be steam, a thick water vapor atmosphere. Deeper down, the pressure increases, and the steam might transition to liquid water, though at such high temperatures, it would be more like superheated steam than the water we know. Deeper still, the pressure might be high enough to create exotic forms of ice despite the heat. The planet might have a rocky core at the center, surrounded by hundreds of kilometers of high-pressure water in various states, topped by a thick atmosphere of steam and hydrogen. 40. Some exoplanets might have rings like Saturn's, beautiful and vast. We haven't directly imaged rings around an exoplanet yet, but we've detected what might be a ring system around a young star called J 1407. If it is a ring system, it's enormous, hundreds of times larger than Saturn's rings, so large that if we placed it in our solar system instead of Saturn, the rings would be easily visible from Earth with the naked eye, dominating the night sky. The potential ring system is about 200 times larger than Saturn's rings, extending to a radius of about 90 million kilometers, roughly the distance from the Sun to Venus. The rings appear to have gaps, possibly carved out by exomoons orbiting within the ring system. If this interpretation is correct, it would be the first indirect detection of exomoons, satellites orbiting a planet in another solar system. The rings are probably young and may be in the process of forming moons, accreting material into larger and larger bodies. 41. There could be exomoons, moons orbiting exoplanets, and some of these moons might be in the habitable zone even if their planet isn't. Imagine a large moon orbiting a gas giant, warmed by tidal heating from its planet's gravity, liquid water on its surface, life evolving while gazing up at the giant striped planet, filling half the sky. This is the situation with several of Jupiter's and Saturn's moons in our own solar system, except those moons are too far from the Sun to have surface water. But imagine a similar moon orbiting a gas giant in the habitable zone of a distant star. The moon would be tidally heated by its constant tug of war with the gas giant, keeping its interior warm and perhaps maintaining a liquid water ocean. The sky would be dominated by the gas giant, a massive sphere striped with colored clouds, showing phases like our moon shows phases, full when on one side of its orbit, new when on the other side. The gas giant would also protect the moon from some asteroids and comets, its gravity capturing or deflecting them. 42. We haven't confirmed any exomoons yet, but we've found tantalizing hints. Detecting exomoons is even harder than detecting exoplanets because moons are smaller and their gravitational effects are more subtle. But we're getting better at this. Every year our instruments improve, our techniques refine, our patience deepens. One way to detect exomoons is to look for additional dips in starlight during a planet's transit. If a moon transits the star along with its planet, it will cause a smaller, separate dip in brightness. Another method is to look for variations in the timing of the planet's transits. A planet with a large moon will wobble slightly as the moon orbits it, causing the planet to arrive at its transit point sometimes early, sometimes late, by a few minutes. These variations are incredibly subtle, but they're detectable with precise enough measurements. 43. The planet Kepler 452b is sometimes called Earth's cousin. It's a bit larger than Earth, orbits a sun-like star, and sits squarely in the habitable zone. Its year is 385 days long, almost identical to Earth's. It's about 1,400 light-years away, so we'll never visit it, never know for certain what it's like. But we can dream about it, imagine walking under a sky that might be blue, might have clouds, might rain water that puddles on rocks. Kepler 452b is about 60% larger than Earth and probably has about 5 times Earth's mass, making its surface gravity about twice what we experience. If you could stand there, you'd weigh twice what you weigh on Earth. The planet orbits a star that's very similar to our Sun, slightly older and slightly larger, but otherwise nearly identical. The star's spectrum would be almost the same as our Sun's, so the light would look familiar, the same yellowy white we're used to. If there are plants there, they might photosynthesize using the same wavelengths of light that Earth's plants use. 44. Kepler 452b's star is older than our Sun, about 6 billion years old compared to our Sun's 4.6 billion. If there's life there, it's had more time to evolve than life on Earth. It could be more advanced, or it could have come and gone already, risen and fallen while light from their world crawled across space toward us, carrying no message, just photons. Earth's life began probably around 3.8 billion years ago, simple, single-celled organisms that took billions of years to evolve into anything complex. If life on Kepler 452b began at a similar time relative to the planet's formation, it's had about 1.4 billion years longer to evolve than Earth's life. That's enough time for an entirely separate trajectory of evolution, perhaps converging on similar solutions to similar problems, or perhaps taking completely different paths. Maybe they have photosynthesis, predation, intelligence, technology. Or maybe they went extinct in a mass extinction event millions of years ago, and the planet is now inhabited by their evolutionary successors, completely different forms that evolved from the survivors. 45. There are planets we call puffy planets or superpuffs. These are worlds with masses similar to Earth but sizes similar to Jupiter, meaning they have extremely low densities, like cotton candy planets. Their atmospheres are so thick and extended that the planet is mostly atmosphere with a small core somewhere deep inside. They shouldn't exist, according to our models. They're too fragile, too easy to strip away, but they're there, defying our understanding, existing anyway. These planets have densities lower than any planet in our solar system, sometimes less than 0.1 grams per cubic centimeter, lighter than styrofoam. We don't know how they form or how they maintain such enormous atmospheres without losing them to space. Stellar winds should strip away such puffy atmospheres over millions of years, yet we observe these planets around stars that are billions of years old. Perhaps they're continuously replenished by outgassing from the interior, or perhaps there's a mechanism we don't understand that allows them to hold on to such diffuse atmospheres despite their low gravity. 46. One theory about superpuffs is that they're young and will shrink over time as their atmospheres erode. We might be seeing them in a temporary state, a brief window in their evolution when they're inflated like balloons before stellar winds gradually deflate them over millions of years. Or they might exist in a particular part of a planetary system where conditions allow them to maintain their puffy atmospheres indefinitely. We might be catching them at just the right distance from their stars, where they're cold enough to hold on to hydrogen and helium, but warm enough to stay inflated. If they migrated inward toward the star, their atmospheres would heat up, expand further, and eventually be stripped away. If they drifted outward, they might cool down and contract, becoming denser. Superpuffs might occupy a narrow zone where they're stable, and we happen to see several of them because that zone, though narrow, exists around many stars. 47. The exoplanet WASP-12b is being devoured by its star. It orbits so closely that the star's gravity is stretching it into an egg shape, pulling matter away from the planet and onto the star. It's a slow process, but in about 10 million years, the planet will be completely consumed, absorbed back into the star it once orbited, a world unborn, reversed. The planet is distorted by tidal forces into an elongated shape, with the long axis pointing toward the star. Material from the planet's outer atmosphere is being pulled toward the star in a stream, forming an accretion disk around the star similar to the disks around black holes. The planet is literally evaporating, losing mass at a rate of about 6 billion tons per second. This sounds like a lot, and it is, but the planet is so massive that even at this rate, it takes millions of years to consume it completely. In the meantime, the star is feeding on the planet, growing slightly brighter and hotter as it absorbs the planet's matter. 48. Watching WASP-12b die tells us something about the fate of planets, about how worlds can end. Not with a bang like a destroyed planet in a science fiction movie, but with a long, slow spiral inward, gradual erosion, a return to the stellar material from which all planets are made. Dust to dust, on a planetary scale. Many hot Jupiters are probably in similar death spirals, just at earlier stages. Tidal interactions with their stars cause them to lose orbital energy, making them spiral inward gradually. Eventually, They get close enough for tidal forces to become destructive, tearing at the planet's atmosphere, then its surface, eventually disrupting the entire planet. The material falls into the star and is consumed by fusion, turned back into energy and light. The atoms that once formed a planet become part of the star, circulating in convection currents, eventually rising to the surface and radiating away into space. Billions of years after the planet is gone, those atoms might be blown off in a stellar wind, drifting through space, perhaps someday being incorporated into a new generation of planets. 49. Some exoplanets orbit their stars backward compared to the star's rotation. We call this retrograde motion. It happens when gravitational interactions with other planets or stars flip a planet's orbit, sending it the wrong way around its sun. Imagine the utter chaos required to reverse a planet's orbit, the gravitational warfare between worlds, the billions of years of slow perturbation, until finally the orbit inverts completely. Or it might happen quickly, in a single violent encounter with another planet or a passing star. Two planets interact, their orbits becoming unstable, and one gets flung into a retrograde orbit while the other is ejected from the system entirely. Or a passing star comes close to the planetary system, its gravity perturbing the planet's orbits, flipping some of them. Retrograde planets are more common than we expected, occurring in maybe a third of hot Jupiter systems. This tells us that planetary systems are dynamic, violent places, especially early in their histories, with planets jostling for position, some being ejected, others having their orbits dramatically altered. 50. There are free-floating planets drifting through interstellar space, worlds without stars. We've detected them by gravitational microlensing, where the planet's gravity bends and magnifies the light from a background star, briefly revealing the dark planet's presence. These rogue worlds might outnumber stars in the galaxy. For every sun, there might be dozens of sunless planets wandering the dark. Most were probably ejected from their birth systems during the chaotic early period of planet formation, when massive planets migrate inward and destabilize the orbits of smaller worlds. Some of these ejected planets are flung out into interstellar space, where they wander forever, dark and cold, lit only by the faint starlight of the galaxy. Others might have formed in isolation, condensing from small clouds of gas and dust that weren't massive enough to form a star. Either way, they're among the loneliest objects in the universe, worlds with no sun, no warmth except what little heat remains from their formation or is generated by radioactive decay in their cores. You're halfway through now. 100 facts is a lot. You don't need to remember them all. You don't need to remember any of them. Just let them wash over you, a catalogue of wonders, a reminder that the universe is fuller and stranger than any story we could invent. Rest your eyes. Breathe slowly. Feel the comfort in knowing that right now, all of these worlds exist, spinning in the dark, whether we think about them or not. Your body is heavy, relaxed, sinking into whatever surface supports you. Your mind is quiet, unburdened by the need to remember or understand everything. These are just stories from the cosmos, whispers from distant worlds, reaching across the darkness to give you peace. 51. The planet Kepler 16b orbits a binary star system, two stars dancing around each other while the planet circles them both. It's a real-life Tatooine. It's cold, though, colder than would be comfortable, a gas giant in the outer reaches of its system's habitable zone. But it proves that planets can form and survive in binary systems, that the universe makes worlds even in complicated situations. The two stars orbit each other every 41 days, and the planet orbits both of them every 229 days. From the planet's perspective, you'd see two suns in the sky, one larger and brighter, one smaller and dimmer. They'd move around each other over the course of 41 days, sometimes close together, sometimes on opposite sides of the sky. Their combined light would be less than what Earth receives from our sun, making the planet cold, its atmosphere probably frozen. But if you could survive the cold, the sky would be spectacular, with two suns creating double shadows, double sunrises, double sunsets, a constantly changing ballet of light and darkness. 52. Planets can migrate. They don't stay where they form. Interactions with the disk of gas and dust they form from, or gravitational interactions with other planets, can cause them to spiral inward toward their star or outward into the cold. Our own solar system experienced migration early in its history. Jupiter moved, pushing and pulling other planets, reshaping the architecture of our cosmic neighborhood. Every system has a history, a story of motion and change. In our solar system, Jupiter probably formed farther from the Sun than it is now, and migrated inward before migrating back outward again. This movement scattered the asteroid belt, sent some asteroids crashing into the inner planets during a period called the Late Heavy Bombardment, and may have been responsible for delivering water to Earth. Saturn, Uranus, and Neptune also migrated, their movements creating the complex structure of the Kuiper belt and scattering objects into the Oort cloud. This migration happened over tens or hundreds of millions of years, slowly reshaping the solar system into its current configuration. 53. The NICE model, named after the French city where it was developed, suggests that Jupiter and Saturn migrated in our early solar system, and their movement scattered smaller planets and asteroids, some falling into the inner solar system, some ejected entirely. We might have had more planets once, lost now to migration and ejection. Computer simulations suggest that most planetary systems probably lose several planets during their formation, ejecting them into interstellar space or sending them crashing into the star. The survivors are the lucky ones that happen to be in stable orbits after the chaos settled down. Earth might have had sibling planets once, additional rocky worlds between Mercury and Venus, or between Mars and Jupiter. They might have been ejected when Jupiter migrated, or they might have collided with other planets and been destroyed. We'll never know for certain, but the evidence from other systems suggests that planet ejection and destruction are common during the formation process. 54. If Jupiter's migration happened today, it could destabilize Earth's orbit. We exist in a stable configuration, but that stability is contingent, dependent on the current positions and orbits of all the planets. Change one thing, and the whole system could unravel over millions of years. We're balanced on a knife edge of gravity, comfortable because the balance has held for billions of years, but not guaranteed forever. Computer simulations show that if you change Jupiter's position or orbit even slightly, the inner solar system can become unstable. Earth's orbit might become more elliptical, experiencing extreme, seasonal variations. Mars might be ejected from the solar system, Venus and Mercury might collide, or Earth might collide with Venus, or be ejected into deep space, or fall into the Sun. The fact that we're here, on a stable Earth with a near-circular orbit, is partly luck, the result of the particular configuration of planets that survived the chaos of formation. 55. Some exoplanets might have global storms that never end, like Jupiter's Great Red Spot, but covering the entire planet. Permanent hurricanes the size of worlds, driven by extreme temperature differences between the day side and night side of tidally locked planets, or by intense stellar radiation heating thick atmospheres. On Earth, hurricanes form over warm ocean water and dissipate when they move over land or cooler water. But on a tidally locked exoplanet, the heat source never moves. The day side is constantly heated, the night side constantly cooled, and the resulting temperature gradient drives perpetual winds. These winds might organize into vortices, massive rotating storms that persist for millions of years, transferring heat from day to night, shaping the planet's climate in ways we can barely imagine. The entire atmosphere might be in constant motion, a roiling mass of clouds and winds that never rests, never calms, a meteorological engine that runs as long as the star shines. 56. The exoplanet HD 80606b has one of the most eccentric orbits we've found, swooping in close to its star and then swinging far out in a highly elliptical path. When it makes its closest approach, its temperature spikes by over 1,000 degrees in just a few hours, creating violent atmospheric changes. Shockwaves racing around the planet as it's flash-heated, and then cooling rapidly as it recedes. The planet's orbit is so eccentric that it spends most of its time far from its star, cold and dim, and then every 111 days it plunges inward, making a close approach that heats it dramatically in a matter of hours. Observations have caught the planet during this closest approach and watched its temperature spike from about 500 degrees Celsius to over 1,500 degrees Celsius in less than 6 hours. This rapid heating creates shock waves in the atmosphere, immense bands of hot gas racing around the planet faster than the speed of sound. The atmosphere expands dramatically, then contracts again as the planet recedes. It's a violent, chaotic process that would make the planet utterly inhospitable to any form of life. 57. We've found planets around stars that are part of dense star clusters, places where stars are packed thousands of times more densely than in our neighborhood. The night sky on such a planet would be breathtaking. Thousands of bright stars visible at all times, never truly dark. Constellations impossible because the stars would be too numerous to see patterns, just a dome of light. In a dense star cluster, the nearest stars might be only a fraction of a light year away, close enough to appear as bright points of light, brighter than any planet in our sky. The combined light from all these stars might make the night as bright as twilight on Earth. There would be no true darkness, ever. Astronomers on such a planet would have a very different understanding of the universe than we do. They'd see thousands of stars with the naked eye, but they'd struggle to see anything beyond their cluster. Distant galaxies, visible to us in dark skies, would be washed out by the brightness of nearby stars. They might not discover that there's a universe beyond their cluster until they developed powerful telescopes capable of blocking out the local stars. 58. In a dense star cluster, nearby stars might pass close enough to a planet's system to disrupt orbits or even steal planets. Worlds could be traded between stars over billions of years, a slow cosmic exchange, a planet born around one star but ending its days orbiting another, adopted by gravity, close. Encounters between stars are rare in our neighborhood, happening maybe once every few billion years. But in a dense star cluster, they might happen every few million years. Each encounter is an opportunity for gravitational interactions that can change planetary orbits. A planet in the outer reaches of one star's system might be captured by another star passing nearby, or a planet might be perturbed into a more elliptical orbit, eventually being ejected from its original system and wandering as a rogue planet until it's captured by another star. Over billions of years, planets might change hands multiple times, orbiting many different stars in their lifetimes, experiencing different types of stellar radiation, different orbital distances, different climates. 59. The chemicals we detect in exoplanet atmospheres include exotic molecules we don't see on Earth: titanium oxide, vanadium oxide, and other high-temperature compounds that only exist in gas form at extreme heat. We're discovering alien chemistry, meteorology that operates on different rules, weather made of vaporized metals. On Earth, titanium and vanadium are solid metals, part of the crust, never existing as gases except in the most extreme industrial processes. But on hot Jupiter exoplanets, where temperatures exceed 2,000 degrees Celsius, these metals boil into vapor and become part of the atmosphere. They exist as molecules, titanium oxide and vanadium oxide, floating in the air like water vapor floats in Earth's atmosphere. These molecules absorb light strongly, heating the atmosphere and affecting its temperature structure. They might form clouds of exotic materials, condensing into tiny particles that rain down as metallic droplets when they cool. The chemistry of these atmospheres is unlike anything we see in our solar system, requiring new models and new understanding. 60. Some hot Jupiters have atmospheres so hot that molecules break down into individual atoms. The concept of chemistry changes at these temperatures. No compounds, just elements in their raw form, atomic soup glowing with heat. atmospheres that are more like the outer layers of a star than like any planet in our solar system. At temperatures above 3,000 or 4,000 degrees Celsius, molecular bonds break. Water can't exist as H2O. It dissociates into hydrogen and oxygen atoms. Carbon dioxide breaks into carbon and oxygen. Even nitrogen molecules, which have very strong triple bonds, can break apart at extreme temperatures. The atmosphere becomes a plasma, an ionized gas where electrons are stripped away from atoms, creating a soup of charged particles. This isn't chemistry as we know it. It's more like the physics of stellar interiors. The atmosphere might glow with its own heat, emitting visible light, making the planet faintly luminous even on its night side. 61. There are planets called ice giants, similar to Uranus and Neptune, made mostly of water, ammonia, and methane ices under high pressure. We've found many Neptune-sized exoplanets. They seem to be one of the most common types of planets in the galaxy. Worlds of deep blue and pale blue, cold and distant from their stars, with internal oceans of strange ices under crushing atmospheric pressure. These ice giants have thick atmospheres of hydrogen and helium, but most of their mass is in the mantle, a deep layer of water, ammonia, and methane in various exotic states. Near the top of the mantle, these materials might be liquid or slushy. Deeper down, the pressure creates exotic forms of ice that remain solid at high temperatures. At the very center might be a rocky or icy core. The planets might have magnetic fields generated by convection in the mantle, where electrically conductive fluids move and create dynamo effects. The atmospheres might have dynamic weather systems, with winds and clouds and possibly even lightning. 62. The planet Kepler 22b was one of the first planets found in the habitable zone of a Sun-like star. It's larger than Earth, about 2.4 times Earth's radius, and orbits its star every 290 days. We don't know if it's rocky or if it has a thick atmosphere, but it's there, in that special zone where water could be liquid, where life as we know it might have a chance. The planet's size suggests it might be a mini Neptune, a world with a thick hydrogen atmosphere and possibly an ocean underneath, or it might be a water world with a deep ocean covering the entire surface. Or it might be rocky with a dense atmosphere like Venus, hot despite being in the habitable zone. We won't know for certain until we can study its atmosphere with powerful telescopes like JWST. But the fact that it exists in the habitable zone makes it a target of interest, a place where we might someday detect signs of life or at least determine if conditions are suitable for life. 63. Every exoplanet discovery adds to our statistical understanding of how common planets are, what types are most frequent, where habitable worlds might exist. We're building a census of the galaxy, planet by planet, learning the rules of planetary formation, understanding the full diversity of what's possible. When we started finding exoplanets, we expected them to look like our solar system, small rocky planets close to the star, giant gas planets farther out, everything in nearly circular orbits. But the reality turned out to be far more diverse. Hot Jupiters close to their stars, super-Earths that don't exist in our system, planets in highly elliptical orbits, planets orbiting backward, planets around binary stars, planets in dense clusters. The diversity is staggering, and it tells us that our solar system is just one possible configuration among countless others. This diversity also gives us hope for finding habitable worlds, because it means nature tries every possible combination, every possible arrangement. 64. Current estimates suggest there might be 40 billion Earth-sized planets in the habitable zones of Sun-like and red dwarf stars in our galaxy alone. 40 billion chances for life. 40 billion places where water might flow, where skies might be blue or green or orange, where something might look up and wonder if they're alone. This estimate comes from extrapolating Kepler's discoveries to the entire galaxy. Kepler found that about 22% of Sun-like stars have Earth-sized planets in their habitable zones. If we apply that percentage to the estimated 100 billion Sun-like stars in the galaxy, we get about 22 billion Earth-like planets. Add in red dwarfs, which are even more common and often have multiple planets in their habitable zones, and the number climbs to 40 billion or more. 40 billion worlds scattered across the galaxy, each with at least the potential for liquid water, each with at least the possibility of life. 65. Even if only a tiny fraction of those 40 billion planets actually have life, we're still talking about millions or billions of living worlds in our galaxy. The Milky Way might be teeming with life, most of it microbial probably, but life nonetheless. Biology expressing itself in millions of variations across billions of years and trillions of miles. If 1% of habitable planets have life, that's 400 million living worlds. If 0.1% have life, that's still 40 million living worlds. And if life is even rarer, say 1 in 10,000 habitable planets, that's still 4 million living worlds in our galaxy alone. The universe has hundreds of billions of galaxies, each with billions or hundreds of billions of stars. The total number of potentially living worlds in the universe is so large it becomes almost meaningless. Life might be everywhere, common and diverse, expressing itself in countless forms, most of which we'll never detect or know about. 66. The Drake equation is a formula designed to estimate the number of active, communicative civilizations in our galaxy. It includes factors like the rate of star formation, the fraction of stars with planets, the number of planets in each system's habitable zone, and so on. Every exoplanet we discover helps us refine these numbers, making the equation less speculative and more grounded in actual data. The Drake equation is n equals r asterisk times fp times ne times fl times fi times fc times l. Each variable represents a different factor: the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life develops, the fraction where intelligent life develops, the fraction that develops technology, and the length of time civilizations remain detectable. We now have good estimates for the first three factors. We know stars form, they have planets, and some of those planets are habitable. The remaining factors are still largely guesswork, but at least we've narrowed down the beginning of the equation. 67. As we discover more exoplanets, we're learning that solar systems come in an incredible variety of configurations. Some have planets all similar in size, evenly spaced. Others have one giant planet and many small ones. Some systems are tightly packed, with planets orbiting closer than Mercury orbits our Sun. Others are spread out across vast distances. There's no single template. The universe experiments with every possibility. Some systems have resonances, where planets' orbital periods are in simple ratios like 2:1 or 3:2. Other systems seem chaotic, with planets in unstable-looking orbits that somehow remain stable. Some systems have planets that are tilted at odd angles relative to the star's equator. Others have planets all in one plane. The variety is endless, and every new discovery challenges our models and expands our understanding of what's possible in planetary system architecture. 68. Planets can orbit stars that are part of binary systems, and we've even found planets in systems with 3 or 4 stars. The orbital dynamics in such systems are complex, like a cosmic dance with multiple partners, but gravity finds a way. Stable orbits exist even in chaotic-seeming configurations. Nature is a better mathematician than we are. In a binary system, a planet can orbit close to one star while the other star orbits far away. Or the planet can orbit far from both stars, circling them as a pair. What's remarkable is that both configurations can be stable over billions of years. In triple and quadruple star systems, the dynamics become even more complex, but stable planetary orbits still exist in specific configurations that minimize gravitational perturbations. The universe has no trouble finding these stable solutions, even when they seem improbable to our mathematically limited minds. 69. The exoplanet 51 Pegasi b, that first confirmed exoplanet around a sun-like star, is slowly falling into its star. It will be consumed eventually, but not for billions of years. It's in a slow death spiral, losing angular momentum to tidal forces, inching inward orbit by orbit, century by century, millennium by millennium. Every time the planet orbits, tidal bulges raised on the star by the planet's gravity dissipate energy, slowing the planet's orbital motion slightly. This causes the planet to spiral inward, very gradually. The process takes billions of years, but eventually the planet will fall into the star and be destroyed. This is the eventual fate of many hot Jupiters, these close-orbiting giants that migrate inward and then continue inward until they're consumed. It's a slow doom, inexorable but patient, taking longer than human civilizations have existed, longer than species survive, longer than continents last, but inevitable nonetheless. 70. Some exoplanets might have magnetic fields like Earth's, protecting them from stellar radiation and solar wind. These magnetic fields would create auroras, like the Northern Lights, possibly more spectacular than anything on Earth, glowing curtains of light dancing in alien skies, green or red or colors we don't have names for, driven by interactions between the planet's magnetic field and its star's energy. A planet's magnetic field is generated by convection in its molten core, liquid, metal, moving, and creating a dynamo effect. Earth has a strong magnetic field that deflects the solar wind, protecting our atmosphere from being stripped away and shielding life from harmful radiation. Exoplanets with active cores might have similar magnetic fields, perhaps even stronger if their cores are larger or their rotation faster. The auroras on such planets might be permanent features at the poles, glowing rings of light that never fade, visible from hundreds of miles away, beacons of the planet's invisible magnetic shield. 71. We haven't directly imaged many exoplanets. Most of what we know comes from indirect methods, from the slight dimming of starlight or the wobble in a star's motion. But the few exoplanets we have directly imaged are revelations, actual pictures of other worlds, tiny dots of light in the glare of their stars, pixels representing entire planets, real places, caught in light and turned into data. Direct imaging is extraordinarily difficult because planets are so faint compared to their stars. A planet might be 1,000,000 or 10,000,000 times dimmer than its star. Seeing it is like trying to see a firefly next to a lighthouse from hundreds of miles away. But with coronagraphs that block the star's light, or by observing in infrared where planets are relatively brighter, we can sometimes capture images of exoplanets directly. Each image is a triumph, a pixel or cluster of pixels that represents an entire world, a place that exists, right now, out there in the real universe. 72. Direct imaging is incredibly difficult because planets are so much dimmer than their stars. It's like trying to see a firefly next to a searchlight from miles away. But we're getting better at it. Instruments like coronagraphs block the star's light, allowing us to see the faint planets nearby. Each direct image is a triumph of engineering and patience. The newest coronagraphs use deformable mirrors that adjust thousands of times per second to compensate for atmospheric turbulence and imperfections in the telescope optics. They create dark regions in the image where the star's light is suppressed by a factor of 1,000,000 or more, allowing planets to become visible. Adaptive optics systems measure the distortions caused by Earth's atmosphere and correct for them in real time. Space telescopes avoid atmospheric distortions entirely, giving even cleaner views. The technology improves every year, and in the coming decades, we'll likely image hundreds or thousands of exoplanets directly, seeing them as they actually are, not just inferring them from their effects on their stars. 73. The planet Beta Pictoris b was directly imaged, orbiting its young star. We've actually watched it move in its orbit over the years, seen its position change relative to its star, confirming that it's gravitationally bound, that it's a real planet in a real orbit. not an artifact or background object. The planet takes about 20 years to complete one orbit, and we've observed it long enough to see it move noticeably. This is one of the few exoplanets where we can measure the orbital period directly by watching the planet move, rather than inferring it from transits or wobbles. The star is young, only about 20 million years old, and the planet is still warm from its formation, glowing in infrared light. It's a massive planet, perhaps 8 or 9 times Jupiter's mass, and it might still be accreting material, growing larger as it sweeps up debris from the disk of material surrounding the young star. 74. Young planets are easier to directly image because they're still hot from their formation. Glowing in infrared light, they shine with leftover heat from the violence of their birth, the collision and compression of material that built them. As they age, they cool and fade, becoming harder to see, settling into the long cold centuries of planetary middle age and old age. When planets form, the process involves countless collisions between planetesimals, smaller bodies that gradually accumulate into planets. Each collision releases energy as heat, warming the growing planet. Additionally, the compression of material under the planet's own gravity releases gravitational potential energy, also as heat. A newly formed planet is hot, glowing dimly in infrared. Over millions and billions of years, it radiates this heat away into space, cooling down. After a few billion years, most planets are cool and emit very little light of their own, making them extremely difficult to image directly. 75. Some exoplanets are so old they formed when the universe was very young, when the galaxy had a different chemical composition. These ancient worlds formed from primordial material, almost pure hydrogen and helium with only traces of heavier elements. They're different from Earth fundamentally, made from an older, simpler recipe, fossils of an earlier cosmic era preserved as worlds. The first stars in the universe contained almost no heavy elements, because heavy elements are made inside stars and distributed when stars die. These early stars were pure hydrogen and helium from the Big Bang. They couldn't have had rocky planets, because rocky planets require elements like silicon, iron, magnesium, oxygen, but later generations of stars, enriched by the death of earlier stars, had enough heavy elements to form rocky planets. The oldest exoplanets we've found are probably gas giants that formed from the relatively metal-poor material available in the early universe. They're ancient, perhaps 12 or 13 billion years old, nearly as old as the universe itself. Let yourself rest here for a moment. Don't worry about how much is left. You don't need to reach the end. The planets will still be there, spinning in their orbits, whether you're awake to hear about them or not. Close your eyes. Let your breathing slow. Feel the gentleness of knowing that the universe is vast and full, that we're learning its secrets one careful observation at a time, one discovery at a time. There's no rush, no deadline. Just the slow accumulation of knowledge, the patient work of understanding, the quiet joy of discovery. Let it wash over you, calm and gentle, like waves on a distant shore. 76. The concept of a habitable zone is expanding as we learn more. We used to think liquid water could only exist in a narrow range of distances from a star. Now we know about tidal heating, greenhouse effects, subsurface oceans, and other mechanisms that could maintain liquid water far outside the traditional habitable zone. Habitability might be more common than we thought, hidden in unexpected places. Tidal heating occurs when a moon or planet is squeezed and stretched by the gravitational pull of a larger body it orbits. This flexing generates internal heat, which can be substantial enough to melt ice and maintain liquid water even in the cold outer reaches of a solar system. Greenhouse effects can trap heat and warm a planet's surface even if it's far from its star. Subsurface oceans can exist beneath thick ice shells, insulated from the cold of space. These mechanisms expand the habitable zone far beyond the narrow ring we originally envisioned, making habitability potentially much more common. 77. Europa and Enceladus, Moons in our own solar system probably have liquid water oceans beneath their icy surfaces, far outside the Sun's habitable zone. They're kept warm by tidal flexing as they orbit their giant planets. If our solar system can have habitable environments in unexpected places, other systems surely do too. Europa orbits Jupiter, and the gravitational pull from Jupiter and the other large moons squeezes and stretches Europa, generating heat from friction in its interior. This heat is enough to melt the ice and maintain a global ocean, perhaps 60 miles deep beneath an ice shell 10 to 15 miles thick. Enceladus, orbiting Saturn, has a similar ocean, venting water and organic molecules into space through cracks in its ice shell. These moons show us that habitability doesn't require being in the traditional habitable zone. Anywhere that can maintain liquid water is potentially habitable, and there are many ways to do that. 78. Exoplanets teach us that Earth isn't the only type of planet that might support life. We used to imagine life would need an Earth-like world. Now we're learning to think bigger. Life might exist in subsurface oceans, in thick atmospheres, in places we wouldn't immediately recognize as habitable. Life, if it's out there, might be more adaptable than we are. Earth's life exists in extraordinary diversity, from bacteria living in boiling hot springs to fish in the crushing darkness of the deep ocean, from microbes in Antarctic ice to organisms in the dry valleys of the Atacama Desert. Life finds a way in the most inhospitable places on Earth, and it might find a way in equally inhospitable places elsewhere. Maybe life exists in the clouds of Venus-like planets, floating in the cooler layers of the atmosphere. Maybe life exists in the atmospheres of gas giants, never touching a solid surface. Maybe life exists in the subsurface oceans of ice worlds, never seeing sunlight. The possibilities expand the more we learn. 79. The exoplanet LHS 1140b is one of the most promising potentially habitable worlds we've found. It's a super-Earth orbiting in the habitable zone of a nearby red dwarf star, about 49 light-years away. It's rocky, it might have an atmosphere, and its star is relatively quiet for a red dwarf, not as prone to violent flares. It's on the short list of places where we might actually detect signs of life with future telescopes. The planet is about 1.7 times Earth's diameter and about 6 times Earth's mass, making it a true super-Earth. Its density suggests it's rocky, not a mini Neptune. It orbits every 25 days, and it probably receives about half the light that Earth receives from the Sun, making it cool but potentially habitable. The star is quiet, producing fewer flares than most red dwarfs, which means the planet's atmosphere has a better chance of surviving. It's one of the best targets we have for detecting biosignatures with JWST or future telescopes. 80. The planet TOI 700d is another promising candidate for habitability. It's roughly Earth-sized, in the habitable zone of its star, and might have liquid water on its surface. It's only 100 light-years away, close enough to study in detail with next-generation telescopes, far enough that the light we see from it left that system in the 1,920 seconds, carrying information about a planet that might have changed in the century since that light departed. The planet is about 20% larger than Earth and orbits every 37 days. It receives about 86% of the energy that Earth receives from the Sun, putting it comfortably in the habitable zone. Computer models suggest it could have a variety of climates depending on its atmospheric composition. It might be an ocean world with a steamy atmosphere, or a frozen planet with an icy surface, or something Earth-like with continents and seas. We won't know until we study its atmosphere, but it's one of the most promising targets for finding signs of habitability or even life. 81. When we detect an exoplanet, we're seeing it as it was years, decades, or centuries ago, depending on its distance. Light takes time to travel. That planet exists right now, this very second, but the version of it we observe is historical, a snapshot from the past, a world that might have evolved or changed in the time its light took to reach us. We're studying history disguised as astronomy. The light from Proxima Centauri b left the planet about 4.2 years ago. The light from TRAPPIST-1 left about 40 years ago. The light from Kepler 452b left about 1,400 years ago, when Europe was in the Dark Ages and the Mayan civilization was flourishing. If we detect signs of life on one of these planets, we're detecting life as it was when the light left, not necessarily as it is now. The civilizations might have risen and fallen in the time the light has been traveling toward us. Or life might have just begun there, too recent for the light to have reached us yet. We're always looking at the past, never the present, constrained by the finite speed of light. 82. Some exoplanets probably have seasons like Earth if they have tilted rotation axes and non-circular orbits. But the seasons might be extreme, far more dramatic than our gentle transitions from summer to winter. Imagine a planet with a 45-degree axial tilt where summers bake entire hemispheres and winters freeze them solid, or a planet with an elliptical orbit where distance from the star creates global seasons of heat and cold. Earth's axial tilt is about 23 degrees, giving us moderate seasons. A planet with a larger tilt would have more extreme seasons. At 45 degrees, the summer hemisphere would receive intense, nearly overhead sunlight for months, while the winter hemisphere would be plunged into bitter cold and darkness. Exoplanets with highly elliptical orbits would experience seasons based on distance from the star. When the planet is at its closest approach, the entire world heats up. When it swings out to its farthest distance, the entire world cools down. These global seasons would be layered on top of axial tilt seasons, creating complex climate variations. 83. The planet HD 209458b, nicknamed Osiris, is losing its atmosphere. The star's intense heat is boiling away the planet's outer layers, creating a comet-like tail of atmospheric gas streaming behind the planet in its orbit. The planet is evaporating, slowly bleeding into space, its mass decreasing year by year, destined eventually to be reduced to just a core if the process continues long enough. The evaporation rate is substantial, about 600 tons per second, though that sounds more dramatic than it is for a planet with a mass hundreds of times Earth's. At this rate, it would take tens of billions of years to completely evaporate the planet, longer than the age of the universe. But the process is ongoing, observable, a slow transformation of a gas giant into something smaller and denser. The escaping atmosphere forms a vast cloud around the planet, extending out to several planetary radii, glowing faintly as it's illuminated by the star's light before dispersing into space. 84. We've discovered planets around stars that have already left the main sequence, red giant stars that have expanded and cooled. These planets survived, their stars becoming red giants, either by being far enough away to avoid being engulfed or by migrating outward as the star lost mass. They're survivors, worlds that endured the death of their suns and continue orbiting the faded remnant. When a star becomes a red giant, it expands enormously, sometimes swelling to hundreds of times its original radius. Planets that were comfortably warm might be engulfed entirely, consumed by the expanding star. But planets farther out survive. The star also loses mass during its red giant phase, blowing off its outer layers in a stellar wind. This mass loss weakens the star's gravitational pull, causing the planet's orbits to expand outward. A planet that was just barely inside the danger zone might migrate outward enough to survive. These survivor planets are fossils, remnants of what the system once was, orbiting a star that's now a shadow of its former self. 85. In about 5 billion years, our own sun will become a red giant, expanding beyond Earth's current orbit. Earth will likely be consumed, but the outer planets might survive, and if they have moons with liquid water, those moons might become habitable as the sun's dying light finally warms them. Death and birth happening simultaneously, habitability shifting outward as the sun dies. Europa, Currently, a frozen moon with a subsurface ocean might thaw completely, its ice shell melting and exposing the ocean to sunlight. Titan, Saturn's largest moon, might warm enough for liquid water to exist on its surface, even though it's currently far too cold. These moons might enjoy a brief period of habitability, perhaps a few 100 million years, while the Sun is a red giant. Then, when the Sun sheds its outer layers and becomes a white dwarf, cooling and fading, the moons would freeze again, their moment of habitability ending, a brief window in billions of years of ice. 86. The exoplanet Kepler 90I is part of a system with 8 known planets, tied with our solar system for the most planets discovered around a single star. It's like looking at a version of our solar system, a different configuration but the same basic idea, multiple worlds sharing a single sun, a family of planets bound by gravity and history. The Kepler 90 system is more compact than ours, with all 8 planets orbiting closer to their star than Earth orbits the Sun. The innermost planets orbit in just a few days, while the outermost orbits in about 331 days. The planets range from small rocky worlds to large gas giants, showing the same diversity we see in our system. The existence of 8 planet systems suggests that planetary systems can be both complex and stable, maintaining multiple worlds in balanced orbits over billions of years. It also suggests that our solar system isn't unusual in its planetary count, that having many planets is common, perhaps even typical. 87. Artificial intelligence and machine learning are increasingly used to find exoplanets in telescope data. The neural networks can identify patterns that humans might miss, finding planets in data that's already been examined and thought to be planet-free. AI is becoming a partner in discovery, teaching us to see what we couldn't see before, expanding our perception. The data from telescopes like Kepler contains millions of measurements, too much for humans to examine thoroughly. Machine learning algorithms can sift through this data, learning what a planet transit looks like, and then identifying candidates automatically. They can detect subtle patterns that human eyes miss, finding planets that are smaller or have unusual orbits. AI has helped confirm dozens or hundreds of previously missed planets in archival data. As our telescopes improve and the data volume increases, AI will become even more essential, perhaps eventually discovering most exoplanets, while humans verify the most interesting candidates. 88. The planet K218b made headlines when water vapor was detected in its atmosphere. It's a super-Earth in the habitable zone of its star. The presence of water vapor doesn't mean there's liquid water on the surface, but it's a step closer to finding truly Earth-like conditions, a sign that the chemistry of life might exist there. The planet is about 8 times Earth's mass and orbits every 33 days. It receives about the same amount of light from its star as Earth receives from the Sun, putting it squarely in the habitable zone. Water vapor in the atmosphere is a good sign because water is essential for life as we know it. However, the planet is likely too large and massive to be rocky like Earth. It might be a mini Neptune with a thick hydrogen atmosphere and no solid surface, or it might be an ocean world with a deep water ocean beneath the atmosphere. Future observations will help determine which it is and whether it could truly be habitable. 89. Some exoplanets might be covered entirely by city-sized hurricanes, permanent storm systems that dominate the entire planet. On a tidally locked world with extreme temperature differences between day and night sides, you'd have constant supersonic winds racing from the day side to the night side, creating perpetual storms that never dissipate, never calm, just rage eternally. The temperature gradient drives fierce winds, sometimes exceeding thousands of miles per hour. These winds organize into vortices, massive rotating storms that might be larger than Earth. Unlike hurricanes on Earth, which are powered by warm ocean water and dissipate when they move over land, these storms are powered by the temperature difference between hemispheres, which never changes. They're permanent features of the atmosphere, persisting for millions or billions of years, reshaping the planet's climate and weather in profound ways. The entire atmosphere is in a state of perpetual motion, never resting, never calm, a world where weather is not an occasional disturbance, but a permanent condition. 90. The study of exoplanets is barely 30 years old. The first confirmed exoplanet around a normal star was in 1995. That's recent history. People alive today remember a time when we didn't know if planets existed around other stars. We've gone from wondering if they exist at all, to cataloguing thousands of them, to planning missions to study their atmospheres for signs of life. It's been breathtakingly fast. In just 3 decades, we've gone from speculation to certainty, from questioning to cataloguing, from wondering to knowing. The pace of discovery has been extraordinary, accelerating year after year as our instruments improve and our techniques refine. Future generations will grow up in a world where exoplanets are taken for granted, where the diversity of worlds is common knowledge, where the search for life beyond Earth is routine science. But for those of us alive now, we're witnesses to this revolution, this transformation in our understanding of the cosmos, this opening of a door that can never be closed. 91. Future missions, like the Habitable Worlds Observatory, are being designed specifically to find and characterize potentially habitable exoplanets. We're moving from discovery to detailed study, from finding planets to reading their atmospheres, measuring their compositions, searching for biomarkers, trying to answer the oldest question, are we alone? These next-generation telescopes will be larger and more sensitive than anything we have now, capable of detecting Earth-like planets around Sun-like stars and studying their atmospheres in detail. They'll look for combinations of gases that suggest biological activity, like oxygen and methane together, or more exotic biosignatures we haven't thought of yet. They'll measure the ratios of isotopes in atmospheric gases, which can reveal whether the chemistry is biological or geological. They'll look for seasonal variations that might indicate vegetation. They might even detect pollution in the atmospheres of industrialized worlds, if such worlds exist. The goal is nothing less than detecting life beyond Earth, or at least determining which planets are most likely to be inhabited. 92. The answer to, are we alone, might come from an exoplanet. Not from radio signals or visiting spacecraft, but from spectroscopy, from analyzing the light filtering through a distant planet's atmosphere and finding chemicals that shouldn't be there unless something is alive and producing them. The discovery might be subtle, a set of spectral lines indicating oxygen and methane together, a quiet confirmation rather than a dramatic moment. When the discovery comes, if it comes, it will probably be tentative at first. A team of scientists will report detecting possible biosignatures in the possible atmosphere of an exoplanet. Other teams will try to confirm the result, looking for non-biological explanations. Debates will rage for years about whether the evidence is convincing. Gradually, as more observations accumulate, the case will strengthen or weaken. If it strengthens, if the evidence becomes overwhelming, the announcement will finally be made: we have detected life beyond Earth. It won't be little green men, it won't be flying saucers. It'll be spectra lines from oxygen and methane, data from a telescope, proof that somewhere out there something is alive, and that will change everything. 93. Or we might find nothing. We might study hundreds of potentially habitable planets and find all of them sterile, all of them empty of life, and that would tell us something profound too. It would tell us that life is rare, precious, perhaps unique to Earth. It would make our planet and all the life on it infinitely more valuable, the only known spark of biology in a vast, sterile cosmos. If we search diligently for decades and find no signs of life anywhere, we'll have to confront the possibility that we're alone, or at least that life is so rare that the nearest living world is thousands or millions of light years away, too far to ever detect. This would be a profound and sobering conclusion. It would make Earth seem even more special, a unique miracle in a dead universe. It would give us a greater sense of responsibility to protect the life we have, because it might be all there is. It would make us the stewards of the only life in the galaxy, perhaps in the universe, at least the only life we know about. 94. But the statistics seem to favor life existing elsewhere. With so many planets, so many potential habitats, so much time for chemistry to experiment and evolution to operate, it seems almost impossible that Earth is the only living world. The universe is too big, too old, too full of possibilities for life to have happened only once. The ingredients for life are common: water, carbon, nitrogen, phosphorus, sulfur, and trace elements. These exist throughout the universe. The processes that lead to life's chemistry, amino acids, and nucleotides forming from simpler molecules, have been observed in laboratory experiments and detected in space. Given the right conditions and enough time, chemistry seems to naturally trend toward complexity. Life might not be inevitable, but it might be probable, likely to emerge anywhere conditions are suitable. With 40 billion potentially habitable planets in our galaxy alone, and hundreds of billions of galaxies in the observable universe, the numbers favor life existing somewhere, many somewheres, scattered across the cosmos, living and dying and evolving on countless worlds. 95. Some exoplanets are so bizarre they expand our imagination. Planets where it rains iron, worlds with atmospheres full of vaporized rock, planets orbiting the collapsed cores of dead stars, free-floating worlds wandering between the stars in darkness. Every discovery reminds us that the universe is stranger and more creative than we expected, that our categories and assumptions are always too narrow. We keep finding planets that shouldn't exist according to our models, hot Jupiters that migrated, superpuffs that defy our understanding of atmospheric retention, diamond worlds that form in carbon-rich systems, lava worlds where rock flows like water. Each discovery forces us to expand our models, to think more broadly, to accept that nature is more inventive than we are. The universe doesn't follow our rules. It follows its own rules. Physics and chemistry operating without concern for our expectations, creating wonders and horrors and oddities that we couldn't have predicted, each one teaching us something new about how worlds can be. 96. The diversity of exoplanets suggests that planet formation is a messy, variable process with many possible outcomes. There's no single right way for a planet to form or evolve. Given the right conditions, you can make almost anything: ice worlds, lava worlds, gas giants, rocky planets, ocean worlds, planets with rings, planets with multiple suns, planets alone in the dark. Planet formation begins in disks of gas and dust around young stars. Small particles stick together, gradually growing into larger bodies. Eventually, you have planetesimals, then planets, but the details vary enormously depending on the disk's mass, composition, temperature, and the presence of other planets. Some planets form quickly, others slowly. Some migrate dramatically, others stay put. Some are disrupted or ejected, others survive billions of years unchanged. The end result is a stunning diversity of worlds, each one shaped by its particular history, each one unique, each one an experiment in what planets can be. 97. Every exoplanet has a history. It formed from a disk of dust and gas, grew through collisions with other planetesimals, possibly migrated, possibly was bombarded by asteroids, possibly developed an atmosphere or lost one, possibly evolved life or remained sterile. Each planet is a story billions of years long, a narrative we're only beginning to read from the faint signals we can detect. We see exoplanets as they are now, or rather as they were when their light left them, but we can infer their histories from their current properties. A planet's density tells us what it's made of, which tells us where in the disk it likely formed. Its orbit tells us whether it migrated. Its atmosphere, if we can detect it, tells us about its volcanic activity, its magnetic field, its interactions with its star. Slowly, carefully, we're piecing together the life stories of these distant worlds, understanding how they came to be what they are, reading their histories in the light that crosses the darkness to reach us. 98. The stars we see in the night sky probably all have planets. When you look up, you're not just seeing stars, you're seeing planetary systems, whole families of worlds orbiting each point of light, places that exist right now, under alien skies, some perhaps looking back in our direction with instruments of their own, wondering the same things we wonder. Every star you can see with your naked eye is likely surrounded by planets, most of them undetectable with our current technology, but there nonetheless. Some might have rocky planets like Earth. Some might have gas giants like Jupiter. Some might have planets we can't even imagine, combinations of properties we haven't thought of yet. And on some of those planets, maybe, just maybe, there's something alive, something aware, something looking up at their own night sky and wondering if they're alone. We're all looking at each other across the vast distances, separated by light years that might as well be infinity, connected by the same questions, the same curiosity, the same wonder. 99. The search for exoplanets is one of the most optimistic scientific endeavors we've undertaken. It assumes the universe is knowable, that distant worlds can be understood, that patience and careful observation will reward us with knowledge. It's an act of hope, looking outward and believing there's something worth finding, worth understanding, worth the decades of effort. We could have decided that planets around other stars, if they exist at all, are too far away and too faint to ever detect. We could have given up before we started, but we didn't. We built telescopes, developed techniques, spent years staring at stars, measuring tiny variations in brightness and position. We persevered through false signals and null results, through instruments failing and budgets tightening. We kept looking, kept improving, kept hoping, and we were rewarded with thousands of new worlds, an entire census of planets scattered across the galaxy, proof that we're not alone in having worlds, confirmation that the universe is even fuller and richer than we dared to imagine. 100, and finally this: you exist on an exoplanet. From the perspective of a distant observer, Earth is an exoplanet, a world orbiting a yellow dwarf star in the outer regions of a spiral galaxy. You're standing on an alien world right now. You're part of the statistics, one of trillions of organisms living on one of billions of planets, orbiting one of hundreds of billions of stars. You're both insignificant in scale and utterly unique in your specific existence, a pattern of atoms and consciousness that has never existed before and will never exist again, here on this blue exoplanet, orbiting this ordinary star, in this quiet corner of space. Think about that. You're on a planet right now. Not just Earth, but an exoplanet, a world that some distant astronomer might someday detect as a tiny dimming in our sun's light. You're part of a living world, one of perhaps billions of living worlds scattered across the galaxy. You're made of stardust, atoms forged in the hearts of ancient stars, recycled through space and assembled into you, temporarily, miraculously. And you're aware of all this. You can look up and wonder about those other worlds. You can imagine them, study them, dream about them. You're a way for the universe to know itself, to wonder at its own vastness, to feel awe at its own complexity. We've reached the end of our 100 facts. You made it, or you didn't. Maybe you're asleep already, dreaming of worlds with 2 suns or oceans hundreds of miles deep. Maybe you're still here, still listening, mind full of planets and possibilities. Either way is perfect. What we've learned tonight, if we've learned anything, is that the universe is generous with worlds. It makes them everywhere, in every configuration, testing every possibility. Rocky planets and gas giants, hot worlds and frozen ones, planets with atmospheres and planets without, worlds orbiting alone and worlds orbiting in pairs, planets bathed in the light of multiple suns and planets wandering in complete darkness. The diversity is staggering, humbling, inspiring. And somewhere among all those worlds, those billions upon billions of planets spinning through space, there might be life. There might be something else looking up, wondering, hoping they're not alone, separated from us by distances too vast to cross, but connected to us by the same physics, the same chemistry, the same carbon and hydrogen and oxygen and nitrogen that makes up our bodies and theirs. All of us made from the ashes of dead stars. All of us, children of the cosmos, trying to understand ourselves. You don't need to feel small in the face of all this immensity. You can if you want to, it's a fair reaction, but you can also feel connected. Every atom in your body was forged in a star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it came from stellar furnaces billions of years ago. You are literally made of stardust. And if there's life on those distant exoplanets, they're made of the same stardust, atoms shuffled differently, but fundamentally the same material, the same periodic table, the same building blocks arranged into different forms. We're part of this. We're not separate from the universe looking in. We're the universe looking at itself, matter organized into patterns complex enough to be curious, to build telescopes, to detect the dimming of distant starlight and deduce from it the existence of worlds we'll never touch, never visit, never truly know, but can imagine, can wonder about, can include in our understanding of what exists. As you drift off to sleep, or as you go about your day, carry this with you gently. You live in an era when we're discovering other worlds. Humans spent millennia wondering if planets existed around other stars, and you're alive at the exact moment in history when we're finding them, cataloguing them, beginning to understand them. That's extraordinary. That's a gift. Sleep well, if that's where you're headed. Rest in the knowledge that the universe is vast and full, that we're learning its secrets slowly and carefully, that there are more worlds out there than we can count, and that each one is real, a place that exists, right now, under skies we've never seen and perhaps never will, but that exists nonetheless, patiently waiting, spinning in the dark, complete and whole and utterly themselves. Thank you for drifting through the cosmos with me tonight. Until we meet again among the stars, this is the Sleepy Cosmos, reminding you that you're made of stardust, and so is everything else, and that's something beautiful to dream about. Good night.